Um, Hi everyone, thanks for being here. And today Bill is going to introduce our speaker. Thanks Bill for doing it.
Well, thank you. Today it's a great pleasure to have Dr. Sarah Stamps here from Virginia Tech. She's an associate professor in the Department of Geosciences at Virginia Tech in Blacksburg, Virginia. Born in Nashville, Tennessee, and discovered a passion for geophysics during high school at Martin Luther King Jr. Magnet School for Science and Engineering. Dr. Stamps earned her bachelor's degree of earth science and minor in mathematics from the University of Memphis, where she graduated magna cum laude. She then conducted PhD studies at Purdue University as a National Science Foundation Graduate Research Fellow and graduated with specialties in geodesy and geodynamics in 2013. Then went on as a National Science Foundation postdoctoral fellow, where she studied at the Massachusetts Institute of Technology and the University of California in Los Angeles. Sarah is now the lead PI on a couple of NSF proposals, an NSF Career Award, as well as the lead PI on an NSF FRES Award to investigate the active dynamics of the East African Rift, involving multiple collaborations and utilizing field-based geodetic, seismic, and geologic modeling. I have a slight connection to Sarah that I'm proud of. That is that my former PhD student, Lucy Flesch, was one of Sarah's advisors during her PhD at Purdue. Hopefully I didn't leave anything out, Sarah. It's mostly accurate, right?
Perfect. Thank you so much, Bill, for the introduction. Well, I'm delighted to be here virtually. Thank you so much for the introduction. Yes, my name is Sarah Stamps. My pronouns are she, her, and I am presenting this talk from Blacksburg, Virginia, where we cannot separate the history of colonialism, slavery, and the forced removal of the Tutelo-Monacan people, who are the traditional custodians of this land. And we pay respect to the Tutelo-Monacan nations and the former enslaved people who lived in this area. So today I'm going to give a presentation on clues about the breakup of the African continent. This work has been highly collaborative with Ella Faraha Saria, who's my colleague in Tanzania, Corne Creamer at the University of Nevada, Reno. Tahiri Rajanarson is my former PhD student, now a researcher at the University of Antananarivo in Madagascar. Also Gerard Rambalamanana in Madagascar and Rui Fernandez in Portugal. So we've, to do this work, we've collected quite a bit of GNSS observations, and the photograph in the background is one of those stations. This is one of our camping stations in northern Madagascar, and it's overlooking part of the Indian Ocean. And in the background, this is an ancient volcano. But this particular site was critical for some of the work I'll be presenting today. This project has also benefited from funding from the National Science Foundation, as well as National Geographic, and we've also received technical support from UNAFCO. My talk today has 5 parts. I'm going to first address fair data principles as an educational moment, and then I'll go through some background information about the East African Rift System. And then I'll talk about a recent paper that came out earlier this year called Redefining the Kinematics of the East African Rift System. And then another paper that addresses the geodynamics of the system on the role of lithospheric buoyancy forces on the East African Rift System, also published earlier this year. And then I'll provide a summary. So fair data principles, these were published in 2016 in a scientific reports paper by Wilkinson et al. And FAIR stands for findable, accessible, interoperable, and reusable. And I want to bring those to your attention just to raise awareness, and that geoscience is really moving more towards the FAIR initiative. So if you produce data or software or models, it is very helpful for reproducibility if you aim to make them fair. In the geosciences, there are repositories like Pangea. This one is a pretty widely used repository for geoscience data sets. Another example place where you could put data, software, or models is Zenodo. It's very general purpose. If you have seismic data, that could go into IRIS. They have the Earth Models Collaboration for seismic and other earth science data. There's also UNAVCO for geodetic data. And then I also bring this to your attention because a lot of journals are adopting the FAIR data principles, like the American Geophysical Union. I believe that Nature has also adopted the FAIR data principles. And if you're publishing your work and you need to find a repository, I'm providing you the website here that helps you to find a repository that might be ideal for your software data or models. So I'd like to acknowledge some of the institutions and organizations that have made their GNSS data available to the public. Many of those are listed here. And these providers, because they made their data fair, have made the work that I'll be presenting today possible. So thank you to those groups. Okay, so let me go into some background information about the East African Rift System. It is the active divergent plate boundary between the Nubian plate and the Somalian plate here. It is quite extensive. So it goes approximately north-south from the intersection of the Red Sea, Gulf of Aden area, 5,000 kilometers to the south to the Southwest Indian Spreading Ridge. And it also extends quite far east-west as well, over 3,000 kilometers from the Eastern Democratic Republic of Congo to Eastern Madagascar. We know the extension rates pretty well. So it's rifting on the order of 1 to 6 millimeters per year relative to the Nubian plate. Each of these red vectors is it's from a previous model, but the rates themselves have stayed pretty consistent. It consists of at least 3 microblocks or 3 minor blocks. And there's actually a newer study that's about to be published by Luke Wedmore that shows there's another plate down here called the sand plate. So I'll be revising this in future presentations when that gets published. But for now, we have constrained at least 3 minor blocks that are shown here. And then I'm going to show you a talk. Part of my talk today will be explaining how this deforming zone has been resolved using geodetic data and modeling. Some other characteristics: it is quite seismically active. This is a subset of earthquakes that are available at the National Earthquake Information Catalog, shown as the red dots for the East African Rift System. And then, of course, it's volcanically active as well. And these are volcanoes available from the Global Volcanism Program. So I will also point out that in blue here, these are all areas that are greater than 1 kilometer in height. So there's actually this quite high topography in Southern Africa and all along East Africa as well. And then one other note about the terminology of East African Rift versus East African Rift System. Most of the time when people are talking about the East African Rift in a publication, they tend to be focused on the continental segment of the broader East African Rift System. So when I'm talking about the East African Rift System, I'm referring to the broader region from the Red Sea, Gulf of Aden intersection all the way down to the Southwest Indian Spreading Ridge. But when I say East African Rift, it's mostly this continental portion of the system. Okay, so let's dive into the first scientific project. So when we talk about kinematics, we're talking about how the surface of the Earth is moving, and then also the geometry of the tectonic plates. These are 2 models of the East African Rift System. On the left here in Stein and Gordon, 1994, they suggested that the entire system was very wide and diffuse, which is represented by this red area and this yellow area. But then a few years later, Chris Hartnedy looked at the distribution of seismicity, which is represented as these gray belts through here. He suggested that there were actually these areas of relatively aseismic blocks between zones of narrow seismicity. So he was suggesting a very different model for how the Nubia-Somalia plate system is breaking up, and that there are actually these minor blocks. So in order to differentiate between these two models, and what we've done over many years is physically measuring the surface motions. So on the left is an example of some surface velocities from Soria's paper in 2014. The black vectors are showing the movement relative to the Nubian plates across the East African Rift system. And then, so using these data, we can invert them, assuming plate rigidity, and then determine if if we can resolve microplates or blocks. And in his paper in 2014, the 3 microplates were again resolved. So the Rovuma plate or microplate, the Rovuma block, sorry, the Victoria plate, as well as the Lawandle block down here. Now, the Global Positioning System is one of many global navigation satellite systems. I'm going to focus on the GPS system today. That's the data that I've processed for this work that I'm presenting. But be aware that there are many global navigation satellite systems. So you may hear GNSS more in the future than just GPS. GNSS is a little more correct. There's systems like Galileo, operated by the Europeans. There's GLONASS, operated by the Russians. There's Beidou, also known as Compass, operated by the Chinese. There's also a Japanese system and some regional ones as well. So GNSS is a much broader encompassing term. So we're using, in this work again, I'll say GPS, and we use this system, these systems, to measure surface motions. So the GPS system in particular, that's the US military operated satellite constellation. And the figure to the left is an example of what that system looks like conceptually. It's approximately 35 operating satellites orbiting the Earth. All of those satellites are transmitting a radio signal down to the Earth's surface, like is imaged in this figure to the left. And then we take that data and we apply the GPS phase equation. And it's a relatively simple equation, and I'm showing it to you to point out that you have to do a lot of corrections in order to really get a millimeter precision position and velocity. In particular, the ion variable here and the TROP variable here. So ionosphere, it causes a delay in the signal. Even though it's electrons, there are enough electrons up there that it causes a slight delay, and we have to solve for that and correct for it. And then also the troposphere, all of the water vapor in the troposphere delays the signal coming from the satellites. There's also some clock errors that have to be corrected for, and some other variables as well, phase ambiguity and some noise. But there's a number of software programs that allow for making these corrections, such as Gamut Globe K, Bernice, Gypsy X. I personally use Gamut Globe K, and that's the program I'll be using for this velocity solution that I'll show you shortly. So once we process the data, we get 1 position per day. Each of these blue circles is representing a millimeter precision position each day with some uncertainties. The x-axis here is time in day of year, and then displacement is along the y-axis here. And we can use the simple velocity equation of distance over time to calculate a velocity from the position data. In practice, these are some examples of the types of instruments that we use to collect the data. On the left is a continuous GPS station. This one is in Uganda. It's fixed in bedrock and it stays there ideally forever, and it continuously records data. Or there's the one on the right, which is campaign data, campaign GPS data. This one is also in Madagascar. We set these up on a benchmark that's positioned in the rock, it ideally stays in the rock forever. Hopefully no one vandalizes it and takes it. And we'll set up the instruments for 3 to 5 days, and then take them down and come back and remeasure the same position over a period of years to get enough data to calculate a reliable velocity. So I wanted to give you a little insight on what it's like when we gather this GPS data. So it's actually, there's a lot of traffic. So this is often the reality here. This is a place in Tanzania where we're trying to get to our stations. Dealing with this terrible traffic is also in other countries as well. We have it happen in Kenya. There we were dealing with cows. Also here we deal with camels. So this also happens. These animals were very slow, you know, we had to be patient with them. And then sometimes we have to deal with very dangerous animals too, like this one.
Move back again. No, they are hungry. Move back a little. Oh, there it is. Now you can open. Now you can open.
That was also in Kenya. But in all seriousness, what we really do with these campaign observations is we explore to find places where we have bedrock, where we have good sky view, and where we also have security. This gentleman in the forefront owns the property where we are now, and he was able to watch our instruments. So we drill into the bedrock, install a benchmark. This is one example. There are many types of benchmarks. And then we very carefully set up our antenna mounts. We level it a lot. We do a lot of leveling to make sure it's very precise, and then set up the rest of the equipment. So we use solar panels to charge a battery, and the battery powers the GPS receiver that's in the box here. It's a waterproof box. And this is a complete setup here. We also weight down the instrument to make sure it doesn't fly away. And then this is an example of a continuous station. This one is here in Tanzania. And we've used here these deep braced monuments where it's mostly ash around this volcano. So we had to do something pretty intense for these stations. So these posts go down like 6 meters each in all directions. And it was quite an adventure getting them installed. But this is an example of one of our stations in Tanzania. And we also have a seismometer here, and this one transmits in real time as well. So we also have a lot of fun. This is one of the students I worked with in Madagascar, being very excited about installing his first benchmark. All right, so once we collect that data, we can ask some questions. These are some open questions that are available that we addressed for this area. So one of the questions was, where is the Lawandle-Somalia plate boundary? This is a map from one of Suria's 2013 papers. Lawandle is here. This is the northern part of the Lawandle block. And the boundary here is going straight through Madagascar. But it's really not a very well understood boundary. This particular paper actually didn't model any stations on Madagascar. And even around this time, there was only one at the time that could have been used. And then another question that has arisen because of some work I published in 2018, I did a strain rate model using GPS data. And that work suggested that the constraints for the Somalian plate motion, which were based on this work, were a little bit too slow. It suggested that the Somalian plate was actually rotating faster than what the earlier estimates suggested. So I'm going to answer those two questions. So let's look a little bit closer at Madagascar. This is part of a geologic map that was produced in 2013. And I've isolated quaternary features, the sedimentary and volcanic features. So there are some quaternary rifts that seem to be active, like the Alautra Anke rift, the Morondava Basin, and then there's the Rannochsetta Shear Zone right here that some researchers have suggested it's also been reactivated and is extending. I'll point out also that there's volcanism. So these red arrows are pointing to these red spots here that are showing quaternary volcanism. And it's been quite interesting. All three of these locations of volcanism started around the same time geologically, which suggests that it wasn't like a plume passing underneath it, or it wasn't this like clear source of the volcanism. So that's still an open question. If we look at the seismicity in Madagascar, these are focal mechanisms from the global centroid moment tensor database. They are suggesting that it is extending. So these are normal faulting events. There's one strike slip event here and compressional event down here. Some more recent work was done by Rakandrabe et al. In 2020. She was part of a project called Makamo, where there was a dispersion of seismic stations across Madagascar and the Comores. So Tsitsi, Rakandrabe's work, she relocated several earthquakes to calculate these focal mechanisms, and then also found in these red circles are all events that occurred over the period that the Makamo network was deployed, which was about 6 years. So she was able to show that indeed it is mostly extensional, as we expect. There were some areas where there's a little bit of compression occurring and some strike slip faults, but dominantly extensional. So there is seismicity across the island. It's pervasive. So we can see the numerous red circles showing the seismicity. And it is pretty complex as well. With respect to the plate boundary, there have been several iterations of where this plate boundary might exist. Kasky et al. In 2010 suggested that most of Western Madagascar is diffuse and deforming. Argus et al. 2011 put the plate boundary along the Rannochsetta Shear Zone, also extended it more northwards and then to the west. Saria et al. This is the plate boundary, also based on one of my earlier papers. And then in 2018, I modeled a geodetic strain rate and suggested that just all of Madagascar was deforming. So these are some, it is not clear at all where this plate boundary exists. To answer that particular question, we're using a new velocity solution. So I processed data for a total of 25 GPS stations across this region and used them in a kinematic model. 16 of these stations are continuous GPS, and they were originally predicted to be on the Somalian plate. So those are shown, those would be some of the red stations, are shown as these red vectors here in the figure to the left. Then there were 5 episodic or campaign GPS stations on Madagascar, and then also 3 new continuous sites on Madagascar that weren't available previously. In this map here, I made the colors to highlight what stations were really new in this work and what hadn't been used in the past in previous studies. And also there was one continuous site on the Comores, which is here, this yellow vector, it's MAYG. This one had not been used in any previous kinematic studies as well. So there is an ongoing event occurring right off of this island here in the Comores. It started in May 2018. So for this site, I did not process any data after May 2018. I stopped it so that it wasn't contaminated by that signal. I did use Gamut Globe K, and I used a 3-step approach following the methods published in Saria et al. And another paper with my colleague Ruiz Yu in 2019. I also used Hector, which is a program that is available to help model the noise. So I could test different noise models, and I used white noise and flicker noise for all of the sites. And then for the continuous sites, I applied the Gauss-Markov equation so that I could do time correlated noise as well with Hector. And then finally, in order to use the data in our modeling, which I'll be showing you next, I required that all of the 1 sigma uncertainties be less than 1.5 millimeters per year. And these are all shown here in this map. To align this work with fair data principles, I did publish the velocity solution in several different ways to make it as open as possible. So it's available as a supplement to the paper. It's also available on Figshare with the model files, and it's available in GMT format, GMT-PS Velo format at UNAVCO. And right now it's at this FTP site. FTP is going away though, so this will eventually migrate to something else. But if you want to grab it from there now, you can. So on to the kinematic modeling that we did. I used tDefNode, which is available at this website here. tDefNode is designed to estimate the angular velocities and also fault locking. And this figure or diagram to the right is showing the elastic blocks would be the blue areas, and then you can define faults as the red areas around those blocks. You have some different functionalities with tDefNode. I used it in a very simple way. So I used freely slipping block boundaries because there was relatively low differences between the velocities on the different blocks. So I used it to do the linear inversion of the GPS velocities to calculate angular velocity vectors. So the kinematic block model, all of the files, all of the input files and also the output files, I made those available on Figshare for open access. That way anyone can reproduce the work. It has its own citation, so if you do use it, I would request that you please use the citation. That would be helpful. This model has 6 blocks. It has a Nubian plate block, which is fixed, Victoria microplate, the Rovuma microplate, and the Antarctica microplate. Their block rotations are all constrained by the previous work of Soria et al. And then I focused on the Lawandle microplate and the Somalian plate. So I re-estimated the Somalia plate rotation, also the Lawandle microplate rotation, and then tested or tried to answer these questions about where that plate boundary is located and also the new rate for the Somalian plate. So in order to address those questions, we first needed a base model of the Somalian plate motions to which we could compare subsequent experiments with. So this base model has velocities only on the Somalian plate, which are shown here. The data themselves are the red vectors, and then the black are the model predictions. So in this one, we calculated a number of statistics so that we could do future comparisons. So the reduced chi-square, the weighted root mean square, and the normalized root mean square as defined in McCaffrey 2005. So for the base model, these are the values up here at the top, 0.7, 0.4, and 0.8. So for the first experiment, we can test if Madagascar moves rigidly with the Somalian plate. So to do that, I added all of the velocities that were on the Madagascar island, and then ran the inversion and got the statistics, and everything degraded. So that's a clear indication that Madagascar as a whole does not move with the Somalian plate rigidly. And then next, I tested each site on Madagascar and the Comoros individually to see if any of those sites were consistent with rigid Somalia plate motion. The Comoros does not move with the Somalian plate, so the statistics are here at the top and everything degrades. And then for each station on Madagascar, there were actually 3 that had similar or better weighted root mean squares, the normalized root mean square or the reduced chi-square, excuse me, the reduced chi-square values. And so the 3 sites that compared well with the Somalian base plate base model were ABPO, this one here, ANTA, and VOIM. So these 3 sites here were consistent with, or are consistent with, Somalia plate motion. So in order, so this figure to the left is showing residuals. So the 3 sites that were consistent with Somalia plate motion are these 2 here, and then this one right here on the edge. And then the other sites were inconsistent with Somalia plate motion. So another, here I've outlined that these areas are not moving rigidly with the Somalian plate motion. And we suggest that this is actually a diffusely deforming zone. And it is consistent with the location of where the seismicity is. So where we have a piece that moves with the Somalian plate, there's actually very low seismicity in that area. So that's suggests that this configuration of Madagascar may be correct. We can also test if this southern piece of Madagascar is moving with the Lawandle microplate. So that's still an open question. And to do that experiment, I brought in a little bit more data. So I brought in data from along the Southwest Indian Ridge. So we have spreading rate data as well as transform azimuth data along the Southwest Indian spreading ridge that can be used to constrain Lawandle plate motion. So I included that data, and then also the 2 GPS stations on southern Madagascar. I need to ask the question if we get a significantly better fit when we include the Lawandle plate. And I do that by using the F-test, which is a way to determine if, when you add additional parameters to a model, if your model improves, is it statistically significant? And this was first used by Stein and Gordon in 1994. They first applied it to tectonic plates. And so I've used that approach as well. So here on the left is a Somalia plate only model. So I've included the data for the 2 sites in southern Madagascar, the 3 that are consistent with Somalia plate motion, as well as the spreading rate data along the Southwest Indian spreading ridge and the transform azimuths. And then on the right is when we add in the Lawandle microplate. And indeed, the Lawandle plate is warranted according to the F-test. And in this figure, I have the Lawandle Euler pole shown as the yellow star, and the Somalia plate Euler pole shown as the red star with 95% uncertainty ellipses. Okay, so a summary of this work is that we did actually find, I forgot to mention that the Somalia plate moves faster than previous estimates. So that did come out of this work. We have a new estimate of the Somalia plate angular velocity vector. And we have a new estimate of the Lawandle Somalia plate boundary location, as well as a new angular velocity vector for that one as well. And here I'm showing the rate. We were able to show that southern Madagascar does indeed move with the Lawandle microplate. And then I was able to isolate this 600 kilometer wide zone of deformation between the Rovuma block and parts of Madagascar. And so this is slightly in contrast to previous work that suggested that the East African Rift system was deforming and separating with just narrow zones of seismicity around aseismic blocks. And here we were able to show that there is this wide zone of deformation also that's part of the system. So it's almost a mix of that early Stein and Gordon model and the Chris Hartnedy model. Okay, so now I'm going to talk a little bit about lithospheric buoyancy forces. And this is work that was published by my former PhD student, Tahiri Rajanarasan. So this work addresses the forces that are opening the East African Rift system. And as a reminder, there's 3 major forces that act on the tectonic plates. Lithospheric buoyancy forces, which are due to variations in gravitational potential energy. And these are caused by topographic gradients and density gradients within the lithosphere. Also, mantle tractions can play a role, and that's the interaction of sublithospheric mantle convection with the base of the lithosphere. And then subduction related forces, mostly slab pull. So Africa is mostly surrounded by spreading ridges, so slab pull is not a major contributor. So the problem reduces down to lithospheric buoyancy forces and mantle tractions across the East African Rift system. So this is a diagram that helps to illustrate those three major forces here. So a little more about the East African Rift. This is, as I mentioned previously, the East African Rift does have some unusually high topography, and that would hypothetically generate large lithospheric buoyancy forces. So in this map, we're seeing topography as this lighter yellow color. And so these are all above 1,000 meters. Something interesting about this work that Tahiri did is that he addressed some newer observations that show there is a northward component of motion in several places along the rift system within the deforming zones. For example, these blue vectors here in the western branch are pointed kind of northwards. There's also a few over here in the eastern branch that have this northwards component. And then also in the main Ethiopian rift up here in the north, there's a northward component. In this map, we also see in yellow, these are predicted motions relative to the Somalian plate or the Victoria block or the Rovuma block. And then the red are the predicted motions relative to the Nubian plate. Now, there has been quite a bit of debate about what are the major forces driving the East African Rift system. There are many authors, including myself, who have proposed lithospheric buoyancy forces are the dominant force. And then other researchers suggest that horizontal mantle tractions more dominate, that there's this upwelling diverging flow from the African superplume that may be driving the system. So we address that in this work here, and I'll go through the topic. So we address the hypothesis of the lithospheric buoyancy forces. So another interesting characteristic about the East African Rift system is that there are some observed strike-slip focal mechanisms, and this is showing evidence for strain partitioning by rift parallel motions. Also in this figure to the left, in addition to the focal mechanisms, which are all strike-slip focal mechanisms, we also see cratonic domains highlighted in purple. And then there's seismic and isotropy observations as well that complicate the story. These red lines here are SKS splitting observations that were compiled by Bagley and Nyblade in 2013. They were proposing here in this figure to the right that the African superplume, which is largely illustrated by the red region here, this is a seismic tomography model, they were suggesting that you have some northward flow from the African superplume that is generating these SKS splitting observations. So there may be some link there. And so we ask one key question: what is the relative role of lithospheric buoyancy forces compared to horizontal mantle tractions in driving observed deformation in the East African Rift? And then we're testing the hypothesis that the east-west opening of the Nubia-Somalia plate system is dominated by lithospheric buoyancy forces. So in order to test this hypothesis, we use the code ASPECT, which stands for an advanced solver for problems in Earth's convection. It's a computational infrastructure for geodynamics code. It uses, the way we've used it, it's the Boussinesq approximation to solve the Stokes flow equations for incompressible flow. So we have conservation of momentum here at the top, and then conservation of mass as well. And the variables are listed down here at the bottom. If you are interested in reproducing this work, we made all of the files available to do that on Zenodo. And then we also provided the output files as well and the input files at the Open Science Framework as well. We had to use two different repositories because when you start diving into finding a repository for your data model or software, there's different restrictions on each of them. So like in order to archive the model output, we needed a place that would allow us to store large files, and that was Open Science Framework. Okay, so the numerical modeling approach has, of course, a number of assumptions. When you do geodynamic modeling, you do have to make many choices. In this one, we chose to use synthetic lithosphere instead of a realistic lithospheric boundary. Although the values we used for the synthetic lithosphere were based on averages from seismically determined lithospheric thickness. So we decided to define the cratons as 150 kilometers thick. So that's the blue areas in this map to the right. The eastern branch is slightly thinner than the western branch. So we defined it as 70 kilometers thick and the western branch as 90 kilometers thick. So that's the yellow. The mid-oceanic ridge is 50 kilometers thick. And then the mobile belts and everywhere else is defined as 100 kilometers thick. We did implement topography at the surface. We used eTopo 1, and that's shown here on the right. The red is higher topography and the blue is lower topography. We applied a second order polynomial interpolation at the surface for the finite element mesh. And then accommodated through deformation, the entire mesh is minimized to minimize the distortion that could cause when you implement topography in a finite element mesh. So we also had variable crustal thickness, and we had 3 different layers. We had the upper crust, middle crust, and lower crust. Upper crust depth is shown in A, and these are all from crust 1.0. B is the base of the middle crust, and C is the base of the lower crust, where all of the blue colors are the thicker areas and the redder orange colors are the thinner areas. We also implemented the densities from crust 1.0 for the upper crust, middle crust, and lower crust. A is the upper crust density, B is the middle crust density, and C is the lower crustal densities. And then for the densities of the mantle, for the mantle lithosphere, we calculated the lithospheric mantle density so that we could have isostatic balance at 100 kilometers depth. So this is the vertically averaged mantle density within the lithospheric mantle. So orange are lower densities and blue are the higher densities. Everything that's below the lithosphere, this model does go down to 660 kilometers. It's a constant 3,300 kilograms per meters cubed. Some other assumptions for the lithosphere domain, we used a conductive temperature gradient based on the equations of Chapman 1986. And then below the lithosphere, we did a adiabatic increase, approximately adiabatic. So for this figure to the left here, this is the geotherm for a cratonic domain. So the base of the lithosphere is 150 kilometers. So we do have that conductive temperature throughout the lithosphere, and then it increases approximately adiabatically below the lithosphere. And then for a rift domain, so here it's a 50 kilometer thick lithosphere, so the conductive geotherm to the base of the lithosphere, and then it increases adiabatically below that. This table down here shows some of the parameters that Tahiri implemented in this model. Okay, also about the viscosity of the system, we used for the crust, it was viscoplastic rheology. For the lithospheric mantle, it was dislocation creep. And then for sublithospheric mantle, we used composite rheology. This figure to the right is showing the viscosity of the system, or the log of the viscosity. So in red, these are the lower viscosities, and we do capture the asthenosphere. And then in blue, these are the higher viscosities. And then finally, more model setup. It is a pretty large model. It's approximately 5,000 by 3,000 by 660 kilometers deep in the east, north, and radial directions. The quadrature finite elements are approximately 40 by 25 by 5 kilometers. We do use temperature fields, compositional fields, and then the velocity fields are also calculated. And it includes the lithosphere, the asthenosphere, and the transition zone down to 660 kilometers depth. So for some results, on the left in A, this is the vertically integrated gravitational potential energy from Tahiri's work. And then on the right in B, this is the same calculation from some work I did using thin sheet modeling back in 2014. So the lithospheric buoyancy forces are quite similar magnitude, but the newer work by Tahiri uses ETOPA 1 and CRUST 1.0. So there's a lot better resolution in the variable gravitational potential energy. These figures show the velocities, and we break it down into two areas, whether it's in the rigid block motion area or the deforming zones. So in the figure to the left, if it's a red vector, these are the predicted velocities from the model. If it's a yellow vector, these are predicted velocities from a kinematic model. So we're considering that to be the observation. So that's the kinematic model from Soria et al. 2014. Also shown here are the root mean square values and the differences in the angular the orientation of the velocities. So when we look at the rigid block motions, we get quite a good fit just from modeling lithospheric buoyancy forces. The RMS is only 0.4 millimeters per year. We're even capturing the anti-clockwise rotation of the Victoria microplate. We capture the clockwise rotation of the Rovuma block with 0.2 millimeters per year and only 10-degree angular velocity difference. And then the Rovuma plate, the continental area, also quite good, an RMS of 1.8, and then an angular difference of 10 degrees. But then if we look at the deforming zones, it's much worse. So we've outlined the deforming zones. They're based on the regions defined in my 2018 paper. So here we don't do that well explaining the velocities, particularly these long rift velocities. So that cannot be explained completely by lithospheric buoyancy forces. We also compared dynamic strain rates with observations we also compared them with the geodetic strain rates of my 2018 paper. So in A, these are the dynamic strain rates from this model in the deforming zones. B are strain rates based on geodetic observations, and then C are the residuals. Blue are areas of low second invariant of strain rate, which is like the magnitude of the strain rate. Red are relatively higher strain rates. So this suggests that the residuals are pretty small in most areas, and it suggests that lithospheric buoyancy forces are the dominant driver of deformation. They don't explain everything, but it does seem to be dominant. So to summarize the geodynamics component of this talk, variations in lithospheric buoyancy forces seem to drive the east-west extension across the East Africa that results from the rigid block rotation. And these findings are consistent with previous 2D thin sheet models of regional deformation patterns. And then across East Africa and surroundings, we suggest that viscous coupling to horizontal mantle flow may actually play a role in driving deformation in the deforming zones. So in these areas that are shown in the figure B. So my final conclusions, this map to the left is showing the work of the geodynamics work that I showed. So those are the black vectors. And then the white are actually the vectors from my recent kinematic model. So I've shown you we have some new constraints on plate motions across the East African rift system, and that variations in lithospheric buoyancy forces seem to drive the east-west extension across East Africa, resulting from the rigid block rotation. And it opens the door to asking a question about the role of viscous coupling to horizontal mantle flow within the deforming zones, because that may be where we have lower viscosity, or we have thinner lithosphere. There could be a bigger role of mantle tractions in that area. So I will stop here. Thank you so much, and I'm happy to take questions. I see some
Thank
claps.
you very much.
You're welcome. And I'll pull up the chat in case anyone wants to post a question in chat. Yes,
yeah,
Hannah.
I can see Hannah already has a question.
Thank you for that very exciting talk. And you presented very clearly all the variables, well, or at least all that you could identify that went into your modeling. And so my question is, since this is not my field of expertise, of all those variables, for example, the assumption of the crustal thickness, the constant density of the mantle, which of those assumptions do you think has the greatest effect? So in other words, if you changed it to a small extent, you might get radically different results.
Okay, I'll make sure I understand your question. Of all the many choices we have to make when we do these models, which choice might have the biggest effect?
Right.
Let's see. Lithospheric thickness is pretty important in how we set up our models. And I kind of think about lithospheric thickness because we vary that quite a lot in many of the other studies that we're working on. And it does play a role. So I would point to that. Also based on previous work, yeah, so I mean, I'm thinking of the geothermal gradient as well, which the way we're setting up the models is dependent on lithospheric thickness. So I don't know, I would point to lithospheric thickness. That would be my answer to that question. Yeah.
Thank you.
You're welcome. Bill.
Yeah, thank you for that talk. I really enjoyed it. I have a question about the dynamics. A couple points or questions. So you have a depth down to 660 kilometers. And did you, as part of your model, include the density buoyancy estimates within the upper mantle and the transition zone? If you included it down to 660, did you include them? And if you did you see the vigorous upwelling related to the fact that tomography shows that you have these areas of low velocity compared to surrounding mantle, and if you convert that to densities, you end up getting a lot of buoyancy. You get a lot of mantle flow. Did you test those types of models with density buoyancies below?
Mm-hmm. So for this specific study, the 2021 paper, we purposely did not include the buoyancy in the deeper mantle. We were very focused on the lithospheric buoyancy forces. We wanted to test, what specifically is that influence. And so we did impose isostatic compensation. So that was through, we forced the lithospheric mantle to have lateral variations in density so that it was isostatically compensated at 100 kilometers depth. However, beyond this study, we have done that work. Actually, Bill, we have done it. That was like third chapter of this student's thesis, which isn't quite published yet. But we did build in that capability to read in a seismic tomography model, convert it to density, and so that we could capture the buoyancy in the sublithospheric mantle as well. And what we found from that was that indeed, when we add the buoyancy from the sublithospheric mantle, we get a better fit in the deforming zones. So it does actually improve the fit in the deforming zones. It doesn't have that big of an impact on the rigid plate motions. Like we still the major parts of the plate seem to be driven by lithospheric buoyancy, but we do get a better fit in the deforming zones when we include the deeper flow.
That's interesting. The result that it's mostly lithospheric buoyancy, I mean, it might be right, but it raises another interesting question about what's going on in the mantle down below. Is, the work I did with Atre Ghosh, and Linjing Wen, when you convert those velocities to densities, you get this very vigorous flow, and it diverges out, and you get large horizontal tractions. And you end up, when you add the GPE component to that, you get this very vigorous extensional system, almost too extensional. And you end up getting problems outside of East Africa. And then later I had another a postdoctoral visiting scientist I work with. We tested 36 different global tomography models, and almost all of them give this really vigorous upwelling. So, what's going on there? I mean, how do you get rid of that mantle flow? We found it to be a really dominant effect, and it's interesting. I mean, there's problems with the assumptions perhaps one is making and converting velocity to density in this type of scenario.
I think it's the viscosity that really makes a difference. So I don't know what if y'all were doing nonlinear flow laws.
No.
Because we are, and I think that's maybe one of the big factors, because when we implement like dislocation creep or the composite rheology, we do get the low viscosity in the asthenosphere, which allows for the decoupling of the deeper mantle flow and the lithospheric plate. That might be one of the major factors, is that nonlinear rheology. Implementing that.
That could be. Real quickly though, your motion prediction for the plates is dependent on your assumed viscosity structure within the plate boundary zones. Did you test the sensitivity of your output plate motion to variations in your assumed flow laws for the plate boundary zone? Because if you stiffen it up, you're not going to get as much spreading, and then you're going to need the mantle. So what's the trade-off?
Yeah, let me go back to this one. So we did impose plastic strain weakening in what we did. We did force it to allow for deformation in the deforming zones. So that was assumed and implemented. I'm trying to think. We did some experiments on like how to define the width of the deforming zone, and eventually decided to use a published paper that has deforming zones. So that's certainly one area that we could explore is varying the width of those deforming zones and see if that changes the plate motions. Yeah. Any other questions?
Well, if no one else, I'll just very quickly, what the heck's going on with Madagascar? I noticed that, what is the topography there is a little higher than I'd realized. It's 2-kilometer elevations. It sort of reminded me of the Apennines. Just the abundance of normal fault earthquakes in the highlands. But I noticed that a lot of those normal fault earthquakes, I think, exist east of where your plate boundary zone is located. So, and it looked to me like most of the earthquakes were located in the landmass of Madagascar itself.
Yeah.
It really looks like a strong GPE signal in Madagascar.
This one.
Yeah, that one. I mean, look at all the earthquakes that lie east of your boundary.
Yeah. Well, I mean, we're proposing a deforming zone. When you say east of the boundary, do you mean
east south,
like these
south of the boundary
down here, like this blue box?
Yeah,
like the blue box.
And mechanism 18 and mechanism 17, 16. I mean, I'm studying it right now, right?
It's complex. It is very complex. Yeah. It is not an easy area to understand. Lots of room there for more studies.
Looks like a GPE signal. Reminds me of the Apennines. Very different setting, obviously.
Well, we're a bit over time.
Yeah.
We should probably wrap up. Okay.
Yeah. Again, thank you again, Sarah, for this very great talk. And I will see you all next week.
All right.
Thanks,
Thank
Sarah.
you.
Thank you.